Hello, everyone. Welcome to this week's Crunch seminar. Today we have one speaker. It's Professor Wei Tai, who is the Clements Chair Professor in Applied Mathematics at the Department of Mathematics at Southern Methodist University. He obtained his bachelor and master's in mathematics from the University of Science and Technology of China in 1982 and 1985, respectively, and he obtained his PhD in applied mathematics at Brown University in 1989. Before he joined SMU in the fall of 2017, he was an assistant and then an associate professor at the University of California at Santa Barbara during 1995 and 1996, and a full professor at the University of North Carolina after 1999. His research interests is in the development of deterministic, stochastic, and machine learning numerical methods for studying electromagnetic, fluid, and quantum phenomena with applications in CFD, metamaterials, nanophotonics, nanoelectronics, biological systems, and quantum systems. His recent work on machine learning focuses on the reduction of spectral bias of deep neural networks with multi-scales DNN and Feynman-Gag formula-based networks for high-dimensional PDEs and optical stochastic control. He has published over 130 refereed research articles and is the author of the book Computational Methods of Electromagnetic Phenomena, published by Cambridge University Press in 2013. And forthcoming book to be published in the spring, Deterministic, Stochastic, and Deep Learning Methods for Computational Electromagnetics. He was awarded the Feynman Prize in Scientific Computing in 2005. Professor Tai, with this introduction, thank you so much for joining us this week, and the floor is yours, and you can start whenever you're ready.
Yes, Juan, thank you for the very nice introduction. And again, that it's always very nice to come back to give a talk at Brown. And today, I'm going to share some of our recent work on developing Martingale neural networks for Hamilton-Jacobi equations for stochastic object control applications. And this is a joint work with a postdoc at Academy Science, China. Shuxing Fang and my former student Weizhang Zhang and Professor Tao Zhou at Academy Science, China. So here is the outline of my talk. So first I will give introduction of this problem. Then I will present the Martingale formulation to solve HJB equations. Then we'll present this SOC-MartNet, this is stochastic object control Martingale network for HJB equations. Then we have some new numeric tests. And then we'll also present some new version of this derivative-free version to avoid computer adhesion for high-dimension problems. Okay, so let's go to the first introduction. So equation one is the problem we try to solve. So this is a SDE with a control, feedback control U, which depends on time and the state of the system, X. And so this problem, of course, is has many applications, and still is one of the very challenging problems because of the cause of dimensionality. And the dimension of X is high, the dimension of the control space is also high. So one of the approaches to study the optimal control is the dynamic programming, which okay, first let's see what we're trying to do. We define this cost functional. So this is the cumulative cost from time t0 to capital T terminal time. And then, so this is the cost function, depend on the control and the state. And there's another one is the terminal cost. And so the SOC-P problem is trying to find a control such that this cost is minimum. Okay, so the formulation of the problem number 4 is very straightforward. It's this. Oh, here I have to mention that because X is a stochastic process, so you have to take the expectation on this state space. Now, to study the this problem, we have two approaches. One is the dynamic programming, and which is involves this value function. So the value function is that if you assume that, so you look at the cost from little t to capital T, and given the state of the system at x, so this actually defines a function, high dimensional function, which we call value function VTX. And this one, of course, will satisfy the HJB equations in the next slide. And there's another approach to study the optimal control problem is the Martingale principle. In this version I give here is so-called verification theory. This tells you how to find optimal control if you know the value function V. Of course, finding the value function V is you have to solve the HJB equation. But this one gives you a way to find optimal control U star, and just you take the increment of all the control kappa, and this identity 5 is point-wise in time and space of time. So you give every t, give every x. X is the trajectory of the system under optimal control. So this one allows you to find the optimal control U star for every t and x. You just have to solve this informal problem. Of course, this problem, finding the informal of this problem is also a cost dimensionality problem because it's a high dimension of the control space. And the Hamiltonian is given by this. It's very, so this is the second order differential, eventually be the differential operator. So this sigma is diffusion of the process, and mu is the drift, and p and z are the joined variables, and c is the cost function. And this h is the key object in our study, also the design of algorithms. So we have to minimize this Hamiltonian h. So next, this is the HJB equation. So you can see from here, this PDE has no explicit formulas because this term requires the computation of the informal of a control space. You only have a few situations you actually has analytical expression for this informal. So to solve the equation 7, you can see there's two sources of cost dimensionality. One is the high dimension of the x. So this PDE is in high dimension. Second, that you have to do the optimization problem of the Hamiltonian for every t and x. Okay, so this is really double whammy for this problem. You have two sources of cost dimensionalities. So our objective to find a numerical method, machine deep learning to take care of both, address both cost dimensionality issues. And so let me first review some existing work. I will go very briefly here. Use machine learning, and the first work actually is by Weinan and his student Hang in very early 2016. Now, their approach actually is a very straightforward approach, just directly minimize the cost function for a discrete system. So the only thing here is that for every time stage in Tn, and they just approximate the control with a neural network, depending on this this state. So this is basically is a very direct application of the deep neural network to do multivariable optimization problems. So this is an important work because this is the first they use this for the control problem, deep neural network, very simple way. But however, this approach has a problem because the neural network are stacked one after another, those neural networks. So you might get vanishing gradient problems if the N is large. And there's another type of work that's related to our approach is use diffusion paths to sample the space, the state space. So this work by Zhou and Han, also Jennifer Lu from Duke, they actually I don't want to go to detail, but the key is that they use diffusion paths to sample the state space. And so the loss function come from this one is a eta formula. And then this is true for any function v, eta formula. Then you just take this as a loss function L1. And then you can find the optimization by optimizing this cost on this function. And the one point I have to make is that in the approach, the diffusion path, the trajectory has to be updated every time the control U alpha is updated. And this actually is something we try to avoid. And we'll see the trade-off of using a path which are independent of the control and the approach with the path with dependent control. You will see their pro and cons in both approaches. Another work also using the actually this one is a little bit different. This one is by the group Peng, you know, the person who did the backward STEs, and this one Peng in Samsung University. So they basically use the joint STEs for the joint variable P. And then you have the optimal control, the last equation here, the minimize Hamiltonian. So they have solved this together. And so this one is related. And there's another one to find optimal control is to take the critical point of the Hamiltonian, but this is a high dimension problem. You also requires this to be a convex function. So this is some work like related to the optimal control. And there, of course, there's some work for solving HJB equations. In most of this work, this by Jerome and George's group with this SDGD, and there's some other work with like this is the last one is maybe like a reinforced learning. All these many of this work are actually for HJB equations where you don't have to compute the informal of the control. So now our approach is that we have two things we have to handle. One is the HJB equation, which is a parabolic equation. And this one, actually, we're going to convert into martingale problems. Then we can construct a martingale neural network. And I think on this part, I gave a talk last December at Brown here too. And then for this optimal control part, we're going to find a way to how to reduce the cost of the minimization of the Hamiltonian. And originally, this minimization for this one is for point-wise t and x. And we found out actually because of this special special form, we can replace this point-wise minimization by an integral form. And so this is a double integral in space and time. And this is, of course, is high-dimensional integral, but this high-dimensional integral can be handled by classical Monte Carlo method. So we avoid one of the cost dimensionality source here because this one, the optimal control you have to do for point-wise. But here is a functional, so we don't have that issue. But still, then you have to do a minimization of the control, the alpha, which is the unit work for the control. So we'll go to I'll give some details now next on both aspects of these algorithms. So the first one is how to do martingale formulation for HJB equations. So actually, we'll present this method for more general, let's call it HJB type equations. So instead, in addition to the Hamiltonian, I have another differential operator L here, which is independent of control. And this one is it was used here because we're going to use the diffusion path with this error as the generator. So in this case, we are going to sample path which is independent of the control. But for what kind of situation you are going to have this extra error here? And this is the several situation you will have that. Now, in case if your control does not appear in the diffusion coefficients, so if your diffusion coefficients is independent of control, then you can put that term out. That second order term will be the error. And of course, the Hamiltonian will be simplified, just have these two terms. So you don't have sigma in this term 16 anymore. Another one, if you know your diffusion coefficients has a lower bound, sigma 0, so it's a perturbation of some sigma 0, then of course you can put this term out. This usually can be done. So you can put this sigma 0 out, and the rest will be your Hamiltonian. Another one is that if you know some approximation to the control U0, and then you can pull a term out LU0. So then the rest will be you subtract one and you take one out. So this Hamiltonian is modified by this. So anyway, that this equation can be you can see in many applications. Okay, now let's see how I can use the Martingale formulation for these HJB equations. So now, see, we have this stochastic process, which is independent of control. Okay, so you have the drift and the diffusion come from this operator L. So this one actually is, we had a paper, 2023 archive paper, is nice under review. And we propose this Martingale new network. This one actually is basically based on the Ito formula. So we know Ito formula basically is a Taylor expansion. So the difference of the, so take any function V, if you have a second derivative in space, then you can do this Taylor expansions. But the thing is that this term will be the generator L plus time derivative. Okay, this is so this one has the second derivative inside, and then you have this term, the Ito integral part. Okay, this term, of course, we know is a Martingale or the Ito integral. So now here you use the PDE, and we know that if you have the optimal control, that's infimum dropped out, so the partial T plus L is minus L H. Okay, so from here you can see this term, this Ito integral is a Martingale. So therefore, I can move everything to the left with define of MTV, which is the Martingale, which just everything except the this term. So this one will be the Martingale. So this actually is the approach of Walladan formulation, Martingale formulation of studying PDEs in the probability theory. So basically, it says MTV is a Martingale is equivalent saying that V is the solution of the HJB equation. So we just have to enforce the Martingale property of this MTV. Okay, so how can we do that? So we have to train a new network V theta such as M V theta becomes a Martingale. So next, so how to find how to efficiently compute the informal? Like I mentioned that instead of doing this minimization point-wise, we just doing the minimization of this functional. And this one actually here, I assume that if the state space of the uncontrolled process contains the state space of the controlled process, and then we can replace this the space variable by xt instead of xt star. So we just have to, therefore, this expectation is taking respect to the PDF transition probability for the xt without control. And this is important. And this allows to us to sample the path pre-calculate before the training. So it's offline calculations to sample the path. And so this is the minimal principal in integral form. And like I mentioned, that this integral can be handled by Monte Carlo integration. Okay, so now we have these two things. The Martingale property is that the average of this m at little t, if we, okay, the average of the Martingale at the capital T, given the condition at little t should be the same as the Martingale as the process at little t. So that's the Martingale property. So we know Martingale is the process modeling fair game casinos. So the money you bring into the casino should be the same when we come out on average. And this second one is the minimal principle. So we have to certify both condition 25, 26. So how to certify 25 the Martingale property? So let's do that. This is the key part, 25. So this is the Martingale property. So the average the increment of the this Martingale given the condition at xt should be 0. Okay, and in our original Martingale neural network, actually we compute this conditional expectations directly by ensemble average. So you just average all the paths. But in this work, actually we try to avoid computing expectations. So we can do that actually by introducing a test function. Because this is a function of xt, it's a 0 function. So this is equivalent of saying that if you integrate by test function in the space-time integral, so this is double integral. So this is equivalent. So 28 is our starting point. But now you will see this condition expectation will be removed because this is double expectations. Let's see how we do that. Because the law xt is the xt measurable, so you can bring this the law inside here. So from 28 to equation 30, we bring that the law xt inside because law xt is xt measurable. Okay, now because now everything is inside, so you have double expectations. We know the Taubert property of condition expectation. Double expectation is the same as one expectation without condition. So now we have equation 31. So you can see now we have this classic Galois formulation. So 32 is a weak form for this Martingale property. So this is going to be our loss function. So we have to have this test function also as a neural network. So we're going to use this idea of weak adversarial network, WAN. This is work by this group. Okay, now this is our loss function. It's very straightforward. So the first term enforces the minimum principle for the control. And so you have to do minimization of the control U. And here you have the value function V is the Martingale property. And you have this test function. So now we can show you some numerical results. So this is actually so the U and the V are processed by two neural networks. So the control has parameter alpha, and the value function has parameter theta. So you do minimization with alpha and theta, you do the maximization of the test function eta. And here is the loss function. So that's how we sample. So you first partition the time. So this is the terminal time. So then, so you generate the diffusion path. You just use the Euler-Moiré scheme. And equation 42, this part can be pre-calculated before training. So it's like offline calculations. So this is very important because this one allows, you don't have to update the path whenever the control is updated. Now the increment of the martingale is just this delta M. Now delta M basically you can see is like a fine difference formula for the HJB equations, but without that error term. Okay, we'll talk about this a minute later. But here, this Hamiltonian does require the calculation of the derivatives. That's the part actually we have to address later on if the dimension is really high, because this is Hessian. Of course, we know this SDGD method is try to address this issue with Hessian. So we also have to address this issue here. So now you can see this integral, like I mentioned, can be used in Monte Carlo space-time. So it's really parallel. So now you can see this is the loss function after you plug in all the samples. So the high efficiency come from two things: offline computation of the sample path, and the second one, the Monte Carlo calculation of the double integral is this one, and this one can be very parallel. So here you just do mini batch and the path index. We have m path. This is time index. Actually, we keep all the time index. So we just do mini batch and the path index. So this is very simple. Actually, what we do is we do two jet steps for descent for the control and the value function. We do case steps of the test functions. We found out just j over 2, our case 2 is enough. So we just fix that. We don't have to mess up with this j and k. And sorry, so for every 2 steps of descent, we do 1 steps of ascent for the test functions. Okay, let's see. Now let's see some numerical results. Of course, if we just saw parabolic equations, you don't have to your loss function just the g part, this part. You don't have to do the control part, minimization part. So it's just this part. So let's just show some numerical results. So this is the number of paths we take 10 to the 5. And the mini batch is like this. Actually, we okay. And those are the learning rates. And j equals 2 and k equals 1, like I mentioned. Actually, we found out the test function network can be very shallow, just 1 layer. And that's good enough. So let's look at, so I just got direct to the HJB equations. Okay, so that's the HJB equations. Now we know this one, the informal actually you can compute analytically, but we pretend we don't know how to compute this informal. So this were HJB equations, of course, corresponding to these control problems. And the control is only on the drift, equation 61. So it's only on the drift. There's no control on the diffusion. And so now see, this is the results, 100 dimensions. Oh yeah, I have to show you the initial conditions, the terminal conditions. We take the very oscillatory. It's very general. Okay, let me show the expression. It's like this. Equation 57 is our terminal condition. So it's not symmetric. It's every direction is like a trigonometry function. It's oscillatory. So it could be very oscillatory by adjusting the frequency. You can adjust this delta to make it very oscillatory. And of course, because at the terminal time, the solution becomes smoother. So because this is a parabolic equation, so we look at this capital T is 0.01, you still have this shape, and the high oscillations, of course, will be smoothed out. And look at the our numerical results. So this is 1,000 dimension, and this is 2,000 dimension. So you can see we got a very nice approximations. And the things about this one is that let's look at the history of the Hamiltonian, because the Hamiltonian has to minimize, and the convergence is very fast. It's only like less than 16 epoch. And in terms of number of SJD learning iterations, less than 2,000. So the Hamiltonian goes settle down very quickly. So that's for different terminal times. And this is the Martingale loss. Okay, so that's for the PDE loss. The Martingale should also go down to 0. Okay, and this is the error. Now, I'll show you this parallel performance. We just, for this result with very old GPU is V100. So we look at the last column. So you can see the 1,000 dimension. When you increase the number of GPUs, times half. So this shows that this method is really highly parallel. Okay, so now this is the part, the first part, where we have to compute the Hamiltonian, which actually involves the derivative of the Hessians. So next one, I will present some results. We just got it a couple of weeks ago. And one of the slides, actually, we just...
yes. Wait, can you go back and explain a little bit the timings, the table, the table,
yeah. So yeah. This is the CPU time.
The accuracy. About what accuracy we're talking about, because
this
I could
that is the 10 to the minus 2 and 10 to the minus 3, like this one. We keep this actually like this. Yeah.
So that's there, 10 to the minus 3. Okay.
Yeah, 10 to the minus 3, yes. So this is the solution you got. So the solid line is the exact solution. The dots are what we have.
Sure. Okay, so in terms of how many GPUs are you using? You didn't say.
Just this 8 GPUs.
So 8 GPUs. So
yeah.
So you're saying 11,000 divided by 10.
Yeah. That's what
so you're saying you have perfect parallel.
Yeah, exactly. This is half. This is. Right. This is twice, right?
But for 10 dimensions, that's not true.
Yeah, 10 dimensions, you have some overhead, I guess. You have to go to high dimension. Yes.
Okay. Then 7. Okay. Yeah. Okay. I see it. Yeah.
Actually, we try to rewrite the code for more than 2,000 dimensions, because, like I said, up beyond 2,000 dimensions, we have problems with Hessian. So that's the one we have to talk about next. So how can I avoid the computation? That's so-called derivative-free version. Okay, so let's answer the question. So how to avoid computing the derivative in this Hamiltonian? So let me first ask the question, what really is our Martingale network for HJB equations? Now it turns out, okay, let me show you the last line. The Martingale network is actually a path density weighted Galerkin method. So that's actually surprising to us. Actually, we found out only 2 weeks ago. So let's see why is that the case. So this is equation 63 is the HJB equation we try to solve. Okay, this is working. We still have this this error term here. Okay, and this U is optimal control, so the information is dropped out. Okay, so recall that the loss function for the network is this term, right? This is the Martingale term. You have a test function. We have this increment of the Martingale. But now if you look at the increment of Martingale, the equation 65, is this the difference plus this term? This actually is the right-hand side of the PDE here. But where is this error term? The error term actually is accounted for by this difference, because this difference by the Ito formula has this generator here, L, and also time derivative T. So you can see that our increment of this term, this increment of the Martingale is nothing but the final difference approximation of this PDE. So this actually is the residue of the PDE. So we are looking at the Galerkin method, but this is weighted by the PDF of this process XT, because you are doing this integral expectation with respect to the process. This random variable has a PDF. So this is a path density weighted Galerkin method. So we go all the big machinery, use the Martingale formulation, Waterdown's Martingale formulation of PDE. Then we use the Martingale property to construct a loss function, and which is this term. And it turns out it's nothing but Galerkin methods. Or we can call it as a weighted, as a weak form of the pin. Okay.
But you still have, yeah, it is a weak form of pins. We have the variational pins.
Yes,
but
exactly.
you still have the, in equation 65, you still have the age.
Yeah. So that's
you still need to compute that.
That's why I'm going to tell you how to avoid that. That's
Okay.
I'm reviewing what we did before.
Okay.
So actually the hint is already here, because you see equation 66. When we do the difference with the process X without control, we got this generator L, right? So this tells me if I replace this X as the process with control, this one will be the generator which is inside this Hamiltonian H. Okay, let's do that. Okay, so now this is our new problem. Okay, I put everything. This is the original HJB equation with this this term LK kappa plus C is the Hamiltonian. Okay, so now we just split it up. This H has two terms. Okay, cost and this generator. Okay. So again, the optimal control is to try to find the minimum of this Hamiltonian, which is L plus C. And the HJB equation becomes a linear equation. That's very important. Okay, what I'm presenting to you now only works for the stochastic orbital control. Okay, it's not for general parabolic PDE anymore. Non-linear will not work. Okay, this is very important. If you know the optimal control, the HJB equation is a linear equation. It's a linear parabolic equation. Okay. Okay, now, so this one is a linear operator because the kappa giving this control kappa. So now let's see. Now, if I apply this control process XU, put this inside V. Now, if we do the Ito formula, you'll see this one will be partial T plus LU. Okay, but we know that from this one, partial T plus LU, you start U. Okay, it's nothing but minus C. Okay, you can see that now. This is minus C. Now we can see this is the Martingale. As before, this is integral. So therefore, now we define a new Martingale. Now you can see this new Martingale has no Hessian. That's the key. So the Hessian is gone. No derivatives are involved at all. So we're going to do a Galerkin method for this Martingale instead of the old Martingale. The old Martingale is this one. This one with a Hessian, with a V and a Hessian, just increment. But now the new Martingale just has V and has a C. There's no derivative of V. So now the Martingale formulation for 69 is that if this is a Martingale, then we solve the HJB equation. And if you use the optimal control. So now again, we follow the same procedure. Now actually again, I still keep one of the uncontrolled process. If we assume the uncontrolled process of the state space as the same as the controlled space, you'll see that why you use that. So now the Martingale property of this one again is this now use the Galerkin method. So we'll arrive at equation 76. This is exact same as before the Galerkin method. Because now the importance is that the increment of the Martingale has no derivatives. It's just equation 77. Just the difference. Okay, now the importance is that this difference, you got random jumps of this one. This jump is the increment of the process, which depends on the control. So that's the price we have to pay. Now, this jumps we have to update when the control U is updated. So now we cannot pre-calculate this because these jumps are sampling the state space. We cannot pre-calculate this offline, the sampling. Okay, how about the another part, the optimal control part?
Also, I think also this is sequential, so you have to wait for the control.
No, we don't do sequential. We do simultaneously. We don't do some. Oh yeah, you mean this one? Yeah, yes. Actually, not. Actually, you'll see that this is another good point. Actually, we are not going to. We actually, yes, see a minute. That we actually make a jump at individual locations. We don't do this sequentially. That's a very good point. We don't do the continuous path of the control path. And I'll show you a minute. Okay, I'll show you a picture. We do like this. Okay, jumps. Okay, how to find optimal control? So this one actually, our goal is to minimize this one. This equation 79. To find the optimal control, you have to minimize this guy. If it's not optimal control, you have to minimize this one. So what we do is that we use you see this is the PDF of the process XT. We actually define the integral of the PDF capital T, capital P. So this one actually, this is integral with respect to little p, the expectation. So now if you do integrated by parts, you get actually just a big pops up. So you have derivative on V. So the time derivative, this is a little trick, plus the end conditions. But if it's the time derivative of V, actually can use the HB equation, is this Hamiltonian. So you can see the Hamiltonian actually is nothing but the time derivative of V. And now, so of course, if the V is not, if U is not optimal control, then you just have to optimize this quantity. So we have to minimize this quantity. So therefore, we have to minimize this one. This one gives us optimal control. And this one gives the Galerkin method for the HB equations. So now our loss function is two terms. The first one is minimized. The first one also has no derivatives. It's just the mean of the V. The second one is the Galerkin, a weak form of the loss function of the Martingale. So now if you look at this, the Martingale, the increment, I'm repeating here, is just the little jumps at X and T. Now, actually, you know what? We just realized, actually, just this morning, yesterday, was this one. You see, if you look at this one has parameter on control and also has the parameter on V. But this one now actually has no parameter on control. So this term, because when we use this PDE HB equation, we use the optimal control. So implicitly, this one has both condition and the minimum principle and the HB equations. So actually, we have a simplified loss function with just this term. But this one we have only tested at least, like 50 dimensions this morning. It works. So we have to do more study on the equations 86. So maybe we can just use this one. So the result I'm going to present you next is all based on 83. But anyway, this one has no derivatives. It does depend on derivatives. So how this method works? So you see, I have two processes. So we'll still use one process xt, which does independent of control. So we just lay like the highway in the state space, laid highways. So you have like the big arteries. So along these big arteries at every discrete location, we make little jumps, But this little jumps is governed by the controlled process. And this is you only need this one to get this Ito formula. When we apply the Ito formula, where did it go? Here. Here. This one, equation 70. So we use this this control process from any point 0 to t to get this this generator with LU. That's how we avoid. So this one uses algebraic equation minus c. That's how we avoided the Hessian. So now you can see that along this path xt, which does not depend on the control, we just make those little jumps. So this is all in parallel. So George, the question to answer George's question that those little jumps can be calculated in parallel. Okay, let's compare these two formulations. The original one, we use we have to have loss. So the new one, derivative free as the MartingNet. The loss function is free of computing the Hessians on derivatives, and they can apply to so the diffusion process is used for exploration, and this one can be any operator. Actually, we choose one actually close to the controlled process, and the price of the derivative-free formulation is that the random jumps are needed to be updated along with optimal control. So this means we cannot pre-calculate it before the training as in the original formulation. So there will be a trade-off. So for one high dimension, maybe the Hessian is more important. For lower dimension, maybe the sample in the past is more important. So we have to figure out where's the crossover point for the trade-off. So now let me just show you the derivative-free results. So this is the 100 dimension, basically same performance as you see. This is up to 500 dimensions. And this is initial data is smooth data. Then we look at the non-smooth data. So this is non-smooth data, initial condition like this. So basically the same performance. Is about this one. Okay, this actually taking more epochs. Let me take it back. This is like 150 epoch. And the original one is only like 15. And the time is that for 1,000 dimension is 900 seconds. 1,000 seconds. And this is 1,000 dimension again. Okay, and this is for different terminal time. And okay, summary. So basically, my time's up, and so there are two papers, archive papers. This is the original. Which one? This one requires computer Hessian. It was in posted on May, and this one actually posted 2 days ago. You can see, it's not divergence free, it's a derivative free. I'm sorry, this is a typo. So the derivative free version, you can also find online now. Those are some other references. Thank you. That's all I have to say.
Thank you so much, Ty. That was a really nice presentation. Do we have any questions from the audience?
Maybe Jerome has some question.
Yes, thank you very much, Wei. Yeah. I have a question from the very beginning when you talk about the, what was your name? The minimum variational principle?
Yes, minimum principle.
Okay. But essentially, if I understood well, and I want to understand that part,
Yeah,
you are simply saying that you have commutation between the integral sign and the minimization. And
yes,
it does commute, right?
Yeah, that's some. Yes, that's true. Yeah, this. Yeah, we maybe we have to. You're talking about this term, right? This integral form, right?
Yes.
Actually, we proved it. There's a proof that we can. This integral minimization can because that function you minimize over is a positive function. Because so that's why you can exchange.
Yes, you can commute.
Yeah, you can commute.
That's one of the key.
Yeah, that's the key. You got the key.
No, I get it. It's actually chapter 14 of the book of Rockefeller on variational convex analysis.
Oh, really?
I'm sure, yeah. So that was more of a comment.
We have
Rockefeller and that.
Yeah, can you send me the reference? Because we have to prove that in our paper to show that this is the point-wise minimization is equivalent to the integral form of minimization.
There are some theorems. I'm not sure about the assumptions that you are using and the one in the book, so I don't know. But yeah, and so it's computation. Okay, that's the key. Yeah,
okay.
That's
right. This is actually very important. Otherwise, we have to do this minimization point-wise, and that's actually is not doable.
Yeah. Okay, thank you very much.
Yeah.
Wei, how much when you go from 500 dimensions to 1,000 dimensions in either of the methods, what is the scaling factor?
Yeah, we have not done all this. We have to do more.
You've done it here. Here, I see the 500 dimensions, and I see 1,000 dimensions. So you have, so there's a factor of 3 times about a 4. So this is like quadratic.
Yeah, 4.
But in the
less than 4, yeah, less than 4.
50 to 100 is linear. Yeah, so it's sort of slightly superlinear, maybe not quadratic. Okay.
Yeah, I really wanted to implement our derivative-free version will hit maybe 10,000 dimensions or higher. Because we have very powerful computer at SMU. We have this super parts.
No, we don't do like, for example, we compute 100,000 dimensions with almost constant going from 250 dimensions to 100,000 dimensions. The cost is about twice as much. So it's almost constant. You just pay for memory. So we're independent of the. We have different ways of doing that, not just the stochastic gradient, dimensional gradient descent, but other methods also. Using the score function, and there's we have published several papers now on that.
Oh, great! Can you send me the reference?
Yeah.
I was cited. And the thing is that I don't know if you can solve this the general control problem where you don't.
No, with the infimum, no, we haven't tried that to do the infimum.
That's our main goal because after we read you guys' paper for the PD itself, you guys solved the problem already. So and I don't think that we can hit the 1 million dimensions. We don't know. We'll try it. We'll after we write our code.
Great.
Do you have any other questions from the audience?
Maybe Sanchin Liu, do you have any questions?
Yes, I can go back to the page 22, the minimum principal part.
Yeah. Yes.
Yeah, can you put a remark on the inclusion of gamma xt?
Yeah,
which is,
yeah. This is actually very trivial because it's mostly for the diffusion continuous diffusion process. They're all just whole state. So this is trivial in most cases.
So basically you need some pre-knowledge of the optimal trajectory.
No, I mean, like I said, if it's they just think it's about Barnett motion. The state space is whole state.
Yes,
So this is equal sign actually. Yeah.
I mean gamma xt is equal to gamma xt
Yeah,
star.
yeah.
You want?
In many cases, but if it's a Markov chain, then we don't know. But
Yeah.
if it's a continuous process, then usually it's whole space.
Okay. Okay, so I'm not sure if you do the numerical test when you're sampling the point, you also need that the trajectory is covering the optimal trajectory or not.
No, you don't have to.
Okay.
Because this is just average, and you just underline continuous distribution. If you sample enough, you are the same thing.
Yeah, okay. Thank you.
So, Giorgio, I think we should talk more because this one is really surprising to us that this actually is it's just like a weighted pin, but the weight has to be the path density.
Yeah. No, that's really a nice interpretation, and it's exactly that.
Yeah, it's very easy for people to understand. Otherwise, before that, this Martingale conditions is very hard to make a link to the PDE itself. But now here it's very clear. You just the final difference, the residue is so actually we call this difference random difference operator, and it's the total derivative in time and space.
Yeah.
The material derivative. Yeah.
Yeah.
Mhm.
Because you follow the particles. Yeah.
Yeah, exactly. Yes. Yeah.
It's like material derivative.
Yeah, exactly.
That's good work. Yeah, excellent. Be ready for a DARPA solicitation on high dimensions, I heard. So,
Yeah. Okay. So let me know if you want me to help you anything. Okay.
Yeah.
Great. Thank you so much, Professor Tsai.
Okay. One thing, Jerome, we need to reschedule a visit. So hope we get a visa.
Yes, I will let you know.
I hope you're not on some special list of United States government.
What do I know?
Okay. Okay.
Okay.
Okay.
Thanks.
Thank you, everyone.
Bye.
Thank you, everyone,
you
for
very
your
much.
time.
Thank you. Thank you for the opportunity.
Sure. Okay. Thank you, everyone, for your time. With this week, we'll close this week's seminar. I hope you all enjoy your weekend.